All right, Chem 120. For this next section, Chapter 4, Section 6, we're going to understand the pH scale and be able to calculate the pH, or the acidity, how acidic or how basic a solution is, from the concentration of hydronium ions in the solution. So we've just been calculating concentration. Now, using that concentration, we can find the pH of something. So we need to measure and use acids and bases over a very large concentration range. And pH and pOH are systems to keep track of these ranges. So these three equations here are going to be really important to jot down. To find the pH, we take the negative log of our concentration of H. H3O plus is also written as just H plus for the concentration of that hydrogen, that proton. pOH is taking the negative log of the hydroxide ions. And it is important to know that if we take the pH of something plus the pOH, it equals 14. So if I ask you, what is the pH of an acid with a pOH of 11? Well, in this case, all we need to do is we know that pH plus pOH is equal to 14. So if I know pOH is 11, that means I can just subtract 11 from both sides and get pH. So pH is equal to 3. What is the pOH of a base that has a pH of 8? So again, if I know the pH is 8, I could say 8 plus pOH is equal to 14. So 14 minus 8. So the pOH is 6. And let's find the pH of an acid where the pOH is 11. Is this the same question? This is the same question as the first one. Well, that's silly. All right, well, it's the same as this. Now, let's look at hydrogen ion and pH simplified here. I want you to get on your calculator and type in the negative log of 1 times 10 to the negative 1, and then hit enter, and you should get 1. Type in the negative log of 1 times 10 raised to the negative 2. You should get 2. Let's do this together. If I type in the negative log of 1, and I'm going to do second e times 10 to the negative 1. Notice how I get 1. The negative log of 1 times 10 to the negative 2 is a pH of 2. So this is concentration of our hydrogen ion. Let's say I did negative log of 1 times 10 to the negative 3. Again, we get a pH of 3. So notice that this hydrogen ion concentration is log base 10. If I did the negative log of 1 times 10 to the negative 11, I should get a pH of 11. So practice putting that into your calculator to make sure that you're getting the right pHs over on the right. Let's look at a couple of problems. So what is the pH of the following? If we're told the concentration of hydrogen is 1 times 10 to the negative 9, we're simply going to do the negative log of 1 times 10 to the negative 9. If you type that into your calculator, we should get a pH of 9. Now this wants me to work backwards. It wants the concentration if we're given a pH of 7. So we need to work backwards here. I have a pH of 7. We want to find this part. So we need to do the opposite of that negative log, which is simply 10 raised to the negative pH will be equal to the concentration. So if I did in my calculator 10 raised to the negative 7, and if you punch that into your calculator, it should spit out 1e negative 7, which means 1 times 10 to the negative 7. And that concentration is molarity. So the pH scale is a scale that ranges from 0 to 14, and it expresses acidity or that concentration of H plus ions that are in solution. And you're probably pretty familiar with this. Vinegar has a pretty low pH. It's pretty acidic, 2.8. Pop is only slightly more than that, 2.9. Orange is more, 3.8. Blood is slightly basic, 7.4. Ammonia, more basic at 11.4. Oven cleaner, even more at 11.7. So again, that's the acidity of H plus ions in solution. So remember, think back to our acid-base neutralization. When we have an acid and a base, let's say HCl plus NaOH, it's going to be a double displacement reaction. And remember, what is the driving force of reactions? To form a precipitate, to form a gas, to form a weak electrolyte. In this case, we are forming water. So our net ionic reaction, again, these are all going to split apart into its ions. I'm going to have H plus Cl minus plus Na plus OH minus, making Na plus Cl minus plus H2O. So we want to get rid of what's on both sides. That would be getting rid of Cl minus, Na plus, leaving me with a net ionic equation of H plus OH minus to give me H2O. So let's look at a couple of problems here. I have 0.25 molar HClO4. Now remember, we want, for pH, is the H plus concentration. Okay, so if I've got HClO4, this is in solution, I'm going to have H plus and ClO4 minus. And how many H's are there? 1. So in 1 mole of HClO4, there's 1 H plus and 1 ClO4. So it's all a 1 to 1 to 1 ratio. So if I've got 0.250 molar of this, I'm going to have 0.250 molar of H plus. So to find the pH, I just need to do the negative log of 0.250. That's the concentration. So let's plug that into your calculator. The negative log of 0.25 should give me a pH of 0.602. All right, moving on to chapter 4, section 7, we're going to use stoichiometry for reactions that are occurring in solution. So before now, we've discussed reactions in solution from a qualitative aspect, right? We know that reactants are converted into products, and with the addition of molarity to our chemistry tools, we can now perform quantitative calculations for reactions. So we can go from volume to moles, moles to moles, moles to grams. since we know molarity, because molarity provides us with how many moles per liter. So we're able to go from a certain volume of something to moles. And we can do the reverse, grams to moles, and moles to volume. So let's look at this example. How many grams of calcium carbonate can be consumed by 35.5 milliliters of, and then we're given a certain concentration of sulfuric acid. So here I'm going from volume of one substance to grams of another. So again, rule number one, we always need to start with a balanced chemical equation. So we need to write calcium carbonate. So CaCO3, we know that that is that equation because calcium is a +2. And if we look at our polyatomic ion sheet, carbonate is a -2. So CaCO3. And we're told that we're combining it with H2SO4. So H2SO4 is my other reactant. All right. So in this balanced reaction, we can see that we have a 1-to-1 ratio here. We're starting with our 35.5 milliliters. 35.5 milliliters. Let's get to liters because we know that this molarity is moles per liter. So there's 1,000 milliliters in 1 liter. That gets us to liters. By writing the 0.125 molar, which is moles per liter, that gets rid of my liters. Notice that they're diagonal from each other. So just by doing that, multiplying my volume of acid times molarity of acid gets me moles of acid. Even think back to this. Molarity is moles divided by liters. So if I multiply concentration by volume, I get moles. If I know moles of my acid, I can get to moles of my calcium carbonate, which is what we did here. We have a 1-to-1 ratio. I want grams of calcium carbonate, so all I did here was my molar mass, 1 mole of calcium carbonate, 2, I added up 1 calcium, 1 carbon, and 3 oxygens to get that molar mass. Why don't you try plug and chug that in and see if you get 0.444 grams of calcium carbonate. So then we're moving on to looking at standard solutions. Some solutions cannot be accurately made by weight and dilution methods if the solute is impure or unstable. So when this is the case, we can make up a solution of approximate concentration and then standardize the solution against a standard compound that reacts with the solute in solution. The standard compound is one that's very stable with a known molar mass that's going to yield a necessary number of sig figs. So to standardize solution, we're going to perform a titration, which we'll talk about here in a second, where we have a measured volume of the solution is added to a known amount of the standard. And then we use an indicator that's added to signal the point where the moles of standard equal the moles of solute reactant. And that's called our endpoint. When this indicator will turn colors when that endpoint is reached. And then if we know moles and volume, we can figure out the concentration because moles divided by volume will give us our molarity. Let's do a couple of practice problems. Given the equation here, we've got sodium carbonate plus nitric acid giving us these 3 products. What mass of sodium carbonate is required for the complete reaction with if I had 25 milliliters of 0.155 molar acid? So I'm starting with volume here. I'm going to start with my 25 milliliters and go to liters. I'm just going to do that in my first step right off the bat and move my decimal point back 1, 2, 3 spots. So 0.025 liters. And this is HNO3. And I'm told the concentration of HNO3 is 0.155 moles of HNO3. per liter of HNO3. And we don't need a number in front of that L, right? Because this unit right here is moles per liter. Oops, I didn't want to cross off moles. Notice that I can cross off liters and liters of HNO3. So now I'm at moles of HNO3. We want to get to moles of Na2CO3. Notice that there's 2 moles of HNO3 for every 1 mole of Na2CO3. And then finally, it wants an ending point of mass. So grams of Na2CO3. And again, anytime we do a molar mass, it's for 1 mole of Na2CO3. And it gave me the molar mass, thank goodness, 106 grams. So let's do our 0.025 times 0.155 times 106, all divided by 2, and we should get 0.205 grams. Try that out, pause the video, see what you get. In this problem, we're going the other direction. It wants to know volume of HNO3 to react with 1.3 grams of barium hydroxide. We're given a balanced equation, and we're given the molar mass of barium hydroxide. So why don't you see if you can work backwards, and then we'll check in. Let's see how you did setting this up. I started with what I was given, though, 1.30 grams of barium hydroxide. So that's my starting point. So if I've got grams, I'm going to go grams to moles using that molar mass that we were given. So this is going from grams to moles of barium hydroxide to cancel out grams. Now I got to have my moles of barium hydroxide on the bottom, and we can see that there's 1 mole of barium hydroxide for 2 moles of HNO3. Now when I do this, cross and cross, that's going to leave me with moles of HNO3. And when I do that, I got 0.01517 moles of HNO3. Now we're told the concentration of HNO3, 0.125 molar. Now remember this, molarity is moles divided by liters. So here I have moles and here I have molarity. We want volume. I've got moles and I've got molarity. So to find volume is moles divided by molarity. So let's do that. 0.01517 moles divided by 0.125. Remember, that's moles per liter. That's what capital M stands for. And when we do that, I get 0.121 liters. But when I look over here at my options, they're all in milliliters. So I just need to convert to milliliters. Remember, that's 3 decimal points the other way. So this is 121 milliliters. This guy. See if you can set this one up. We've got an aqueous solution of sodium chloride, and it gives hydrogen gas, chlorine gas, and sodium hydroxide when an electrical current is passed through the solution. So here is our formula. If we begin with 10 liters of 0.15 molar sodium chloride, what mass of sodium hydroxide can be formed? See if you can get there. So first thing that I saw, since I'm given liters of sodium chloride and concentration of sodium chloride, I go, oh, if I multiply these two together, I'll get moles of sodium chloride. So let's do that first. 10 liters of NaCl times 0.15 moles per liter of NaCl gives me 1.5 moles of NaCl. All right, once we have moles of something, we can get to moles of something else, and we want to get to sodium hydroxide. So let's do our mole to mole ratio. It's a 2 to 2 ratio. Cl needs to go on the bottom to 2 moles of NaOH. And we want, what do we want? The ultimate is we want mass. So I'm going to say 1 mole of NaOH. We need to find the molar mass of 1 Na, 1 O, and 1 H, which should be 40 grams NaOH. So we're going to do 1.5 times 2 times 40, all divided by 2. And we should get 60 grams of NaOH. Oh, not that one. This one.